Hello there! In this video, I'll be giving a few examples on how to make more complex functions in GBG, such as exponents, logarithms, and roots, which all make use of loops in the frame system of GBG. So let's begin. So first things first, I want to talk about the frame system of GBG. So if you're not familiar already, GBG runs on 60 FPS, or in other words, 60 frames per second. It basically means everything in the game only happens 60 times per second. That's the smallest amount of time that can happen between things in the game. However, that's not entirely true for all of the nodons. So here on the right, I have put all of the middle nodons that rely on the frame system. So all of these nodons only look at their inputs every frame and only change their outputs every frame. So for example, if we take this counter here and say let's put a constant 1 here, since the counter relies on the frame system which runs at 60 frames per second, if we put a 1 at its count-up input, what would happen is 60 times a second, the counter will look at its input and see that there's a 1 there and add a 1. So you can see here, while it's going up really quickly, what's actually happening is every frame, 1 is being added to the counter. On the other hand, here on the left, I've put all of the nodons that actually don't rely on the frame system. So basically, all of these nodons can calculate their outputs instantly and don't have to wait every frame to change their values. So for example, if I put this counter here and connect this output to all of these nodons like this, and let's put a counter order here and put a button on the counter. As soon as the value of the counter changes, every single one of these calculations is done instantly, and its final value will show up here on the exact same frame that the counter changes values. So with this in mind, basically all of our calculations will be done using all of these nodons, and all of these nodons on the right, including the counter, is basically just used to store numbers and values between calculations. With all that being said, let's begin with our first function. So the first function that I want to discuss is the exponential function. So for example, we have a number and we want to raise it to a certain power. So for example, 2 to the power of 7. So 2 to the power of 7 is basically just 2 multiplied to itself 7 times. And if you do that, you will get the number 128. Now, of course, the most basic way to do this calculation is to just take our original 2 and maybe get a few maps and multiply it by 2 multiple times. So 2 to 7, so this is 2 to the 1, 2 to the 2, 3, 4, 5, 6, and 7. So if we wire all that up together, you'll get 128, same as what we had here before. Now, the problem here is, well, first off, we're using a ton of nodon to do this. And secondly, this setup is very rigid in that this only works specifically for 2 to the power of 7. What if we want to calculate 2 to the power of 10 or 2 to the power of 12 or 13? This setup won't work anymore and we need to add more maps or multiplications to do that. So is there a better way for us to calculate the exponential of a number? Well, if you think about it, what we're doing is very simple. We're just taking our number and multiplying it by, in this case, our number 2, multiple times repeatedly. So let's see if there's a way for us to do that in GBG. So first, let's start with a counter, set to 1. Let's say we want to multiply this 1 by a certain number, for example, 2. Well, to do that, we can take this counter here, multiply it by 2, and we will have our volume. So thinking about loops, what we want to do now is to take this output 2, put it back into this counter, so that when we look at the output of this multiplier again, it's now going to be 2 times 2, which is going to be 4, and we can just keep repeating that again and again until we get our desired value. So how do we get this number into our counter? Well, right now, the problem is our counter has a value already. So even if, say, we put a multiply nodon over here, and then we have a button here to activate it. So basically what's happening here is we're taking our value here and then sending this value into the counter. You'll get 1 plus 2 is equal to 3. So instead of changing the counter value to 2, we just added the counter value. So what do we actually need to do? Well, the simplest way to do this is to simply, instead of sending to itself, we can also send the current value of the counter and then send it to countdown and basically subtract it from the counter. And we can just wire this button down here. So what will happen now is when I press this button, what will happen is this one is going to send here, this multiply and send to the countdown. So the counter will go back to 0. And at the same time, this signal will go here, get multiplied by the current output of the multiply here, which is 2, and get added into the counter. So basically what happens is the counter goes from 1 to 0 to 2. You see here, it works just like that. And now that we have this system set up, every time we press this button, it'll just do the same thing. Whatever is the values in the counter here, it gets deleted by this multiplication here. And then the value here multiplied by 2 gets put back into the counter. So every time we press the button, we get 1, 2, 4, 8, 16, and so on. And now, for example, if we want to calculate 2 to the power of 7, all we need to do is simply press this button 7 times. So 1, 2, 3, 4, 5, 6, and 7. And now we'll get 128. Now what we want to do is to make this thing automatic. Instead of us pressing a button, we just want it to do the calculation on its own. So for now, we can maybe do something like this. So let's put a timer here. And instead of the button, we connect the timer to these multiply nodons and just have it run on a constant. So now this thing will do the multiplication on its own. But now the problem is it'll just keep going. But right now, the system has no idea where we want to stop. So let's try to figure that thing out. First, we can put a counter here. And this will basically act as our index for our system to count how many times it has done the calculation. You see here, as it multiplies this number, this basically shows how many times this number has been multiplied by 2. Now let's say we have another constant here which says the power that we want to use. So for example, we want to calculate 2 to the power of 7. We just put a number 7 here. And the way that we can tell the system to stop doing the operation once it reaches a certain number is we can just basically take a comparison here, have it check if the index is less than the number of times we want here. So here, as long as the number of times that our system has done the calculation is less than the number of times that we wanted to do it, this signal will stay on. So what we can do is simply just take a AND nodon, AND it with this signal, and that signal with this timer, and use this added signal instead to activate our system. So now you'll see is that at the start is all gonna do the same thing normally, but the moment that this counter reaches 7, this comparison turns off and this AND turns off, which means that even if this timer is counting up, our whole system has completely stopped and settled on the value that we want, which is basically 2 to the power of 7. And we can just test it for any other value here. So for example, here we want to calculate 2 to the power of 10. And we can just run this whole thing again and wait till the counter reaches 10, and we will see that it will successfully be able to calculate 2 to the power of 10, which is 1024. And since the multiplier that we're using here is just based on this constant, we can even change this constant to whatever we want. Let's say 5, and let's change this number to like 4. So here is going to multiply the number here by 5 4 times, which is basically 5 to the power 4, and we'll get exactly that, which is 625. So now we've basically made a very simple exponential calculator in GBG. So right now our calculator here is a bit slow. Basically right now, if we set the exponent to 4, it will basically take 4 seconds for this whole thing to calculate the final value, since we need to wait for this timer to activate 4 times. So how fast can we make this timer? If I say set this to 0.1 seconds, you see that it still works perfectly fine. if you think about it, why do we actually need to wait for this timer to activate? What values do we need to settle before we send a signal to this counter? So basically, what we need for the calculation to work out correctly is for this comparison neuron to turn off when this counter is at a certain value, and also for this calculator neuron to have the correct value that it wants to send into the counter. But as I mentioned earlier, all of these neurons don't rely on the frame system. They can calculate their values instantly, and the only thing that they need to wait for is the counters here. So actually what we can do is basically take away this timer, and even take away this and we can just connect this comparison straight into these signals, and you will see that our whole system will still work perfectly fine. And for example here, I change this value to whatever I want. You will see that it will still work completely fine and no problems at all. This is because every frame, as soon as the value of this counter changes to the next value and this counter comes up to the next value, this next value and the state of this comparison will be calculated immediately. So the only thing that we're waiting for is for the next frame, for these counters to move on to the next value that they're going to go to. And with that, we now have our basic exponential calculator in GBG. Now, there's still a few things that we can improve with the system. Now, this system may work for the first values that we put into it, but a problem that it still has is that it has no way to reset its values. So to illustrate that, for example, let's say we have a counter here and set this to an initial value of 8. So here is able to calculate the value 2 to the power of 8 correctly. But if we try to change the value after it's calculated that, for example, let's put it here, try to change this to, let's say, to 7, it's not going to change anything since the value in this counter has already gone up. To fix this, all we need to do is to send a signal to the reset of these counters so that every time we reset them, it will recalculate this value again. So for example, if we change the value of this exponent down to, let's say, 5 and reset the counters, it's now going to be able to calculate 2 to the power of 5. And it's going to do this as many times as we want whenever we press this A button. Now, what if we want our system to do this resetting automatically without having to wait for the player's go signal on when it should try to recalculate the inputs? Well, what we can do is, well, we know that the system will be finished doing its calculation when this comparison neuron is off. So what we can do is simply just take this not neuron, connect it to this comparison, and we would know that if this not neuron is activated, that means our system has finished calculation and we can reset these counters to do the calculation again. Now right now you might be seeing a problem. So while it does do the calculation correctly, like if we stop this counter at the exact moment when this not neuron is activated, it will be at the correct value. However, since we're resetting it every time that it reaches the correct value, our output here basically never stays constant at the correct value. So while it does react correctly whenever we change the value of our inputs, the signal that's going out of this counter is not really useful since, well, we're not sure which of these values is the correct one. So what we basically need to do now is to have another counter and basically save the value of this counter only when the value of this counter is the correct value. So let's try to do that. So we know that when this not neuron activates, this counter has reached its final value. So what we can do is simply take this multiplication neuron, take our counter value, and so this not. Now you can see at the very first frame, while we have this counter set to 6, it does correctly send 2 to the power of 6, or in other words 64 here. However, now we encounter a problem where, well, since it's repeatedly recalculating, this counter is just going to keep adding that same value again and again. So what we need to do is, instead of adding this value to the counter, we want to replace the value in this counter. And for that, we really did the same thing with this first counter that we had here. So if you still remember, all we need to do is take another multiplication node on here, take the current value of the counter, and then send it to the countdown, so that whenever this signal wants to go into the counter, we send the same signal here to essentially reset the value of the counter, just as the value of this calculation node on tries to enter the counter node on. So now when we do this, you see that it stabilizes to the value that we want. And even if I change the value of our exponent in real time, every time I change it, during the next calculation loop of this counter, this not only is going to send a new signal to tell this counter to change its value to whatever value is inside here. So now we have a live, fully working exponential number calculator. Now, if you want to shave a bit more nonce, one thing you can realize is that instead of having this multiply node on here, getting the value of the counter and sending it to the countdown, another thing that we can do instead is, instead of doing this, we can just send a constant -1 into this input. And it basically does the same thing. So why this works is basically, instead of sending 2 over output minus 1 over output, that's essentially the same as saying just adding 1 over output to our current output. How you do that is by just subtracting this by 1. Now let me just clean this up. Here we have the full code for a basic exponential calculator, where this is the base of our number and this is the exponent of our number. And if you want to clean this up a little bit more, another thing you can do is replace this multiply node on here and instead have a subtraction node on. Connect this value here and just try to subtract part of the subtraction node on. That is here. We're basically just moving the addition and subtraction to this node on so that we only need to do one multiplication into the counter. So now that we have this exponential function, it's actually very easy to derive another function that's called the factorial. So if you're not familiar with the factorial, factorial is basically just multiplying all of the numbers until a certain point. So for example, 4 factorial is 1 times 2 times 3 times 4, which rounds out to 24. And then 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120, and so on and so forth. Now if we compare that with our exponential function here, let's say 3 to the 5, what we're doing is 3 times 3 times 3 times 3 times 3. So to get the factorial, which is 1 times 2 times 3 times 4 times 5, all we need to do is basically just replace this 3 with a counter that counts how many times we've multiplied already. In this case, we already have that, which is this counter right here. So all we need to do to get a factorial function from our original exponential function here is, first we just set this counter to 1 so that at the very start it multiplies by 1. Then let's connect our value here where the base used to be. And now you're seeing that if we input our 5 here, we get 24, and 6 we get 120. So it's still 1 off. Since we're expecting at 5 factorial is going to give us 120 and 4 factorial is going to give us 24. So here it's not doing the last step. And that's because we're still using a less than comparison here. And what's happening is, for example, here when this value reaches 4, our system has only multiplied 1 times 2 times 3 and then stops. So what we want to happen instead is that once the value of this counter reaches 4, we want it to still do one more iteration of this before this comparison turns off. So to do that, we simply just set this to less than and equal, so that what happens here is that this value gets multiplied by 1, then 2, then 3, and then lastly 4, and then this count, and then 4, at which point this comparison will then turn off and then stop running the loop. So this is our simple automatic factorial calculator. Now the next function that I want to talk about is the logarithm, which is basically the inverse of our exponential function. So for example, we have 64, and we want to get the log base 2 of it. So that's basically the same as asking how many 2's multiplied together are inside this number. So for example, here with 64, we know that 64 is 2 to the power of 6. So if we put log base 2 of 64, that should give us 6 because there's 6 2's multiplied together inside this number of 64. So let's try to make a function to do that calculation. But before we did multiplication, now let's try division. So let's say we want to divide the value of this counter by 2. To do that, we just take a division node on, awesome 2, and we want to replace this counter with this value here. So we do the same thing that we did earlier, where we have a multiplication here and another multiplication to cancel out the value of the counter. The first one here to cancel out the value of the counter, and the second one here to add the value that we want into the counter. So if I press this button to activate both of these multiplications, we get this result where basically it takes the current value of our counter and divides it by 2. Now here we're able to do the repetitive division, but how do we get the output of the logarithm from here? Well, from here, I see we just need to count how many times we do this division until our number becomes smaller than our base. For example, here, if we're trying to get the log 2 of 64, we can divide it once, twice, thrice, 4 times, 5 times, and then finally 6 times. And we're at the number 1, which is less than 2. So we know that there's only 6 2's inside of our original number 64. So to automate this, all we need to do is to get a comparison node on here. And what we want to happen is for this counter to increment and for this loop to divide the current value of the counter by 2, as long as the value of our counter is greater than or equal to the base that we want. So we just replace this button with this comparison. Here, you see that, just like that, we're able to calculate the log 2 of our value here correctly. Let's say let's change it to 32. Calculate it's 5. 33 is still 5, and we go down to 31. It goes down to 4, since after dividing 31 by 4 times, it's already less than 2. Now here we have a new problem that wasn't present in the exponential function. Here this currently works, but this is because we literally store our value that we want to calculate from inside the counter. But what if, let's say, the number that we want to get the logarithm of is outside the counter and can change anytime? For example, 128 over here. What we need to do now is to find a way to inject this value into this counter at the start of the loop in order to calculate the logarithm of this number. So again, we want to replace the value inside this counter. So we do the same thing that we did before, where we can just take a multiply node on and have a button tell it when to do it. And at the same time, when we press this button, what we want to happen is for the current value of the counter to be subtracted from the counter. And for that, we could make another multiplication here and connect it here. But we actually already have the exact same multiply node on here, so we can just simply connect this to this counter as well. So now what will happen is every time we press this button, this counter goes back up to this value that we have in our input here. And if we want our counter here to reset correctly, all we need to do is connect this A button into this counter as well. So now every time I press the button, our value is first stored into this counter, and then our counter here at the output gets reset. Every time I press the button, it does the calculation correctly. Now, if we want to do the same thing as with our exponential function, where it updates in real time, well, we know that the calculation is done when this comparison turns off. So all we need to do is, like before, get a not node on, connect it to here, and replace this button with our not node on, so that every time this not node on activates, it essentially does the same thing as activating the button. And like before, we have the same problem where our counter keeps repeating again and again. So we need to do the same thing with the exponential function and have another counter here to basically store the final value of every iteration of this counter. Just take a negative that, set it here, our multiply node on, multiply to the counter, and our signal to store the value here into here. So now you can see that we now have a fully working logarithm calculator, where this is the base and this is the value. For example, we put 256, it gives us a value of 8. And if we try to raise the base, for example, log base 3 of 256, that is 5. This is basically the least number of nodons that you need in order to implement this. But if you want to clean this a little bit up, one thing that you can realize is that this multiply is actually on all the time, because whenever this comparison is on, it's setting the signal. Whenever this comparison off, it's also setting the signal. So basically, we're constantly sending signal of the counter here. So we can just remove this and replace it with an additional one to basically send this counter value back into its countdown. Or we can also use an invert node and send it into the count up, depending on which you prefer. So now we have a perfectly automatic logarithm calculator, with this input being the base, this constant being the actual input, and the output of our function being this counter. Now, this last part of the video is going to contain a bit of math, so be warned if you're not prepared for that. So this next section of the video is going to contain a bit of complex math, so if you're not a fan of that, you've been warned. So now that we've basically unlocked loops in GBG, this actually gives us access to one of the most powerful equation solving algorithms out there, which is called the Newton-Raphson method. So what the Newton-Raphson method does is that it can basically convert most complex equations to a much simpler operation that we just need to repeat again and again and again, which will cause our output to get closer and closer to the real value. So here I've basically implemented a square root function without using the square root node on, and by only using a counter and very simple calculations. So just to show it to you, here's the square root node on, and here's its output. And you can see that its output is exactly the same as whatever input that we put here. Now with one caveat, the square root is able to calculate square roots immediately, since it's one of those nodons that don't rely on frames, while here, it goes through a few steps before it gravitates to the correct answer. For example, here, see there, it takes a few frames before the counter ends up in the correct value 27.37. Now, of course, there's no reason to do this for implementing a square root, since we already have the square root node on here. But I'm just going to use this as a basic example on how to use the Newton-Raphson method, which I will show later how we can use to unlock other functions that used to be impossible to do in GBG. So let's dive right in. So here is the gist of the Newton-Raphson method. The Newton-Raphson method states that given a certain function, f of x, where f of x is equal to 0, if we have a random guess for the value of x, let's say x1, and then we do x1 minus f of x1 over f prime of x1, so basically the derivative of our function here, the difference of these two values will result in a value x2 which is closer to the real value of x. So for example, we have a function where the real value of x is, let's say, 1, and then our first guess is 10. What will happen here is if we put 10 here as x1, maybe x2 will become maybe something like 7. And then when we put 7 here, it's going to go to like 5, then 3, then 2, then every time we do this equation again, the value of our x gets closer and closer to the real value of 1 until it eventually hits it. But to make it easier to understand, let's just start with an example. Let's say we want to figure out the square root of any value. So let's say our value that we want to get the square root of is a. The first thing we need to do is to make a function using this that is equal to 0. To do that, all we need to do is to make a function from here that doesn't use the square root and is equal to 0. To do that, all we need to do is to just square both sides. We get x squared is equal to a. Then move a to the other side. We now have x squared minus a is equal to 0. So now, since this equation is equal to 0, this can be our f of x. So f of x is equal to x squared minus a. And then f prime of x is basically just the derivative of our function here. So the derivative of x squared minus a is 2x plus 0, since a is just a constant. Now let's try to run the Newton-Raphson method. Remember, Newton-Raphson method is basically doing this equation again and again and again until we get a final answer. So let's try to use this with these two functions, x squared minus a and f prime of x is 2x. So this is what our equation will look like in this case. And if we try to simplify our equation further, we can end up with the equation x2 is equal to x1 minus x1 over 2 plus a over 2x1. Let's try to run the iterations. So let's say, remember, a is the number that we want to get the square root of. So let's try to approximate square root of 2. So we set a is equal to 2. And then our first guess for x1 can be anything. Let's just start with 1 by default. So when we try to do this equation for the first time, with our guess as 1, so now remember, we know that the square root of 2 is equal to 1.41. Let's see how accurate this algorithm is. Let's say we start with our first guess as x1 is equal to 1. If we plug in x1 and a here, we're going to get this equation, which is 1 minus 1 half plus 2 over 2. And if we do this, it'll basically get 1.5. Now, if we run through this equation again, but now with x1 as 1.5, we get this equation. And if we try to solve it, we're going to get 1.42. And then if we put 1.42 again in our equation, try to solve it, we're finally going to get 1.41. You see here, in only 3 steps, 2 iterations of the same function we had earlier, we're able to figure out the square root of 2. And if we take a look back up top, you notice that this equation is actually exactly what I did here. So this equation x2 is equal to x1 minus x1 over 2 plus a over 2x1. Actually, another way to represent this same equation is here. Basically the same as x2 is equal to x1 plus minus x1 plus a over x1 over 2. And if you take a look here, remember x1 is basically our current value. Then x2 is what we want our next value to be. So if we want to get from x1 to x2, all we need to do is basically add this entire term into our current counter in order to reach x2. And that's what I did. So here we basically have negative x1 using this inversion, add to this map, plus a, which is the thing that we want to get the square root of, divided by x1. So we just take x1 and divide a by that value. So now we have negative x1 plus a over x1. Then we just have this map divided by 2. And then we just add that back to the counter. And by just converting this equation into these nodons, we're basically able to solve for any square root that we want. Now we can actually go back to our original equation here and generalize it for basically any root, not just square roots. For example, cube roots, fourth roots, fifth roots, and so on. Basically, we just do the same thing that we did here and just replace n with whatever root that we want. For example, we want to solve for the cube root, so x is equal to cube root of a. What we'll just end up here is a function of f of x is equal to x cubed minus a, and f prime of x is equal to 3 times x to the power of 3 minus 1, or basically 3 times x squared. And basically that's what I did over here, which calculates for the cube root. If you try to solve the equation to something similar to what we did here, what you'll eventually end up with for the Newton-Raphson equation for finding the cube root is x2 is equal to x1 plus negative x1 plus a over x1 squared over 3. And that's exactly what I did here. It's x1 plus negative x1 plus a over x1 squared is x1 squared divided by 3. With this, we can solve for the cube root of basically any number. And we can just change this n to any root that we want to create a function for basically any root in GBG in only a few nodons. And actually over here, I've taken this whole equation one step further, and I've basically generalized it for basically any inputs. So now instead of hard coding these equations for specifically like square roots or cube roots or fourth roots, here, well, f of x is just x to the power of n minus a, and f prime of x is just n times x to the n minus 1. But if you remember earlier, I already showed you how to make exponential functions in GBG. So instead of hard coding the squares and such, what I did was basically just take the entire exponential function and put it inside here and have it calculate the function in real time here, and I can change the degree of the root and the input to whatever I want. For example, here, the fourth root of 81 gets calculated to 3, and I can change it to, let's say, 361. The fourth root of 361 is around here, 4.36. I can change the degree as well. Like the cube root of 361 is 7.12. So that's a brief introduction to using the Newton-Raphson method to solving almost any equation in GBG. Now, with all the functions that I showed you in this video, the biggest caveat to all of them is the fact that it takes them a few frames to reach their final output. For example, here with our exponential function, let's say we want to calculate maybe 2 to the power of 10 to the power of 9. You see that our function here takes a few frames to calculate this value. And this is because we are limited by the timing of the counter, since the counter can only do one multiplication per frame. Now, using normal GBG logic, this is basically the fastest that we can go. But in GBG, there's actually a way to do multiple calculations in one frame. And this is by using a mechanic called subframes. Now, subframes is a topic that we don't have enough time for this video, and it'll probably be the topic of another video. But for now, I just want to show you these same functions that we did today using subframes. So here's an example for a subframe exponent calculator. So here it works the same as earlier. We have a base and an exponent here. But unlike before, where this would probably take 16 frames to execute, here you can see that the output here gets calculated instantly. And this is because we completely remove all the counters here, and we're only using these nodons, which can theoretically calculate things instantly. Now, I won't explain step by step how it exactly works, but the main concept is basically the same of what we did earlier, just in the subframe context. So for example, here up top, we have the module which counts how many times the operation has been done. And we have here our comparison, which checks if that number is still less than the exponent that we want. And then here we have the multiplication. And here is where the number is stored, and this is what's multiplying it for each iteration. These are the knots which reset the whole system every time it reaches the final value. And so we have a similar module here, which stores the final value of the operation every time this goes through the loop. Now moving on down, we have the same thing for the logarithm. So this is a subframe logarithm calculator. You see it works the same as before. Input of 128 and base of 2. It gives us the answer of 7 almost instantly. And basically it works the same way. Our input is initially stored in a module here. And then the value that's stored in here gets divided by our base multiple times. And we have a comparison here which counts the number of times that we've divided so far and stores it into a module here. Here's the knots which reset the whole thing every time a loop finishes and reaches a final value. And here we have the same module which stores the final value that is calculated so that the value here does not change. And even for the Newton-Raphson method, I did the same thing. So I copied the subframe exponent calculator here over here and put it into the nth root calculator that we had. So now even for very, very complex computations, like for example, 81 to the 26th root, our whole system here is able to calculate the final value in just a few milliseconds. And that is where I'll leave you for today. So thanks for watching and see you in the next one.